So in the previous sections, we have discussed how to represent any given complex number graphically on an argan plane. We have also worked on a few problems where we have determined the modulus and the argument of the given complex number. So in this section, we are going to talk about a different way of representing a complex number, and it is called the polar form. So this is going to be another alternate form of a complex number. So for this, we are going to consider a non-zero complex number z equals to a plus ib. Non-zero meaning that the value of a is not going to be equals to 0, so is the value of the imaginary part of the complex number b, which is also not going to be equals to 0. Now we know that this complex number, if we draw the argan plane, let's assume that this point A and B are both positive, then it's going to lie somewhere on the first quadrant. Let's call this as point A with the coordinate values A, B. So what we can do here is we can represent it by this point by the polar coordinates r and theta instead. So what we are going to do, we're going to draw a straight line from the origin to the point A, and we are going to name it as the radius. So the radius is going to be a positive value originating at the origin, and it goes to the point A. It's going to be a straight line. So let's assume this as the radius of the complex number. Then we look at the other parameter, which is the angle that the radius makes with the positive direction of the x-axis. So this is the angle theta. So given a complex number z, a plus ib, so we are going to express it in the polar form. So polar form, that means we are going to write in terms of the radius r and the angle theta that it makes with the positive direction of the x-axis. So let's look at the geometry of it, how we deal with it. So we have the line OA, so we are going to drop a perpendicular line from the point A to the real axis, and let's call it as point B, where it meets the real axis. We are also going to drop another perpendicular line from point A on the imaginary axis, and where it meets the imaginary axis, we are going to name it as point C. Now let's consider the right triangle. In the right triangle, which is right angle at B, so we have ABO. So let us find out the value of sine theta. So our sine theta is given by the perpendicular, which is AB, over the hypotenuse, which is OA. Now we are going to substitute the value of AB by the actual measurement along the y-axis or the imaginary axis, and we know that this value is B. So we have B over OA. So OA is the radius, so here it will be substituted by R. Now what we're going to do, we're going to cross multiply, and that will give us the value of B, which is equal to simply R times sine theta. So this is the value of B. Now we'll find out the value of cosine of theta in the same triangle. So cosine of theta is given by the base, which is OB, divided by the radius, which is OA. So that means OB, the value of OB is going to be equals to the distance of point B from O, which is simply A. So we have A over OA, which is the radius. So upon cross multiplying, we get A is equals to R times the cosine of theta. Now let us substitute this value into a complex number z equals to a plus ib. So that gives us z is equals to a, which is R times cosine of theta, plus I times b, and b is R times sine theta. Now we factor it out since it's the common factor in both the first term and the second term. So we have R multiplied to cosine of theta plus I times sine theta. So this is the polar representation of the complex number z, a plus ib. So let us do one example. Before doing an example, let me mention one fact: the similarity of the polar form with the graphical form that we talked in the previous section. So here r is equivalent to the modulus of the complex number z, and theta here is same as the argument of the complex number z. So this z, which is written as r times cos theta plus I times sine theta, is just another way of representing a given complex number using only two parameters, which will be the radius and the theta, which is the argument of the complex number. So let us take an example now. So let's say given a complex number 1 plus I times root 3. Now we know that this complex number lies on the first quadrant. So this is going to lie in the first quadrant. That's because the real value as well as the imaginary value are both positive. So when both the real and the imaginary parts of a given complex number are positive, then they are going to lie in the first quadrant of the argan plane. Now we have to find out the radius. So the radius r is simply equals to the absolute value of the complex number z, which is going to be equals to the real part, square of the real part, added to the square of the imaginary part, which is root 3 squared. And that should give us 1 plus 3, which is equals to the square root of 4, and that gives us 2. Now we're only going to consider the positive value of the square root. That is because radius being a positive distance. The radius, so we're considering that our radius, the value of our radius r, lies between 0 and infinity. So it's always going to be a positive number. So now that we have the value of the radius, let's try to find out the argument. So argument, for finding out the argument, first we have to determine the acute angle alpha, which is simply equals to the tangent inverse of the imaginary part, which is root 3, divided by the real part, which is 1. So we have tangent inverse of root 3. And we know that the tangent of 60 degrees, which is pi over 3, has the value of root 3. So that means we can replace root 3 by tangent of pi over 3. So that gives us tangent inverse of 10 will go away, and that will leave us with pi over 3. So we have theta, which is simply going to be equivalent to the argument of the complex number z, is going to be equals to alpha, the acute angle alpha, because our complex number lies in the first quadrant. So that means this implies that the value of theta is simply equals to pi over 3. So in the polar form, we'll have z is equals to r cosine theta plus I times sine theta. So we're going to replace r by its value, which is 2 here. So we have 2 multiplied to cosine theta. So cosine theta is pi over 3 plus I times sine pi over 3. So this is the required polar form of the given complex number z, 1 plus I times square root of 3. Now the thing is, if we find out the value cos pi by 3 and sin pi by 3 and then multiply it by 2, then we should get exactly the complex number 1 plus I root 3. So this is just another way of representing the same complex number z, 1 plus I root 3, in the polar form. So if we are to find this complex number on the argan plane, so what we're going to do is, first let's draw the argan plane. So we have the real axis, which will be the real part of z, the imaginary axis, which is simply going to be the imaginary part of z. Now we are going to draw a radius, a line which is going to have an angle, which is going to have a length of 2 units, and it's going to make an angle of pi over 3 So pi over there, that's not a straight line. Let me draw a straight line. So this is going to be 45 degrees. So let's tilt it above. So this should be approximately 60 degrees. So we have theta equals to 60 degrees, and assuming that this radius is exactly equals to 2 units. So this gives us the complex number, and if we try to find out its coordinate value, then what we can do is we can drop perpendicular lines on both the real axis and the imaginary axis, and then from here we can find out that this value is going to be exactly equals to 1, and this value is going to be equals to the square root of 3. So this is another benefit of plotting a complex number on an argan plane by using only the two parameters, which is the radius as well and the angle theta.